and welcome back to SciByte, everybody, where we explore the mysteries of the universe and all the tools and technology that science is using to get to the bottom of it all. And I am, after taking a 2-week hiatus, happy to be back as your host, Jeremy. And joining me on the Skype line, the same as every week, even when I'm not here apparently, is Heather.
Hi, guys. This week, we're going to take a look at crazy science questions. The weird, the wacky, the too strange to be true, until science intervenes. We'll break it down and serve it up and see what it all means.
And most of these actually came from our chat room when we pitched the idea a couple weeks ago. Now, previously on a SciByte episode, I think the last one that I was actually on, we pitched that one of our upcoming episodes would be about quantum mechanics.
Yes.
And I want to tell you that we put a lot of research time into it, a lot of brain effort, but there's a good reason that we're not going to be going forward with that. But to find out, you're going to have to watch this entire episode of SciByte because we have an important announcement to share with you at the end of the episode.
So stick around.
That's all business, though. Before we get down to business, let's have a little fun with these questions, why don't we? The first one was one of the first ones that actually prompted us to do this entire series of questions. It was that one of our viewers had seen a video of a floating strawberry. No strings, no water, no nothing. Well, a little bit of water, and we'll tell you why about that. But basically, he wanted to know, how the heck do you float a strawberry?
You may have seen the strawberry. Some people have seen crickets or frogs or even mice. But it's all due to diamagnetic properties.
Say what?
Diamagnetic properties. It's a property of an object that causes it, when a magnetic field is applied to an object, it alters the way the electrons move, the way they orbit, so it kind of creates an opposing force, kind of like the north and north magnets that you remember may have been playing with.
Most people that are interested in science, which is probably why you're watching the show, you play around with magnets on occasion, and if you get two of the same pole together, they push each other apart. You can't make them stick together.
Yeah.
So what you're saying is that when you apply a magnetic field to certain materials, they in essence start to generate an opposite magnetic field just by their composition?
Yeah, water is one of these materials. Most of the time, it's a very, very, very weak field. So you put a strawberry on a magnet, it's just going to sit there.
Sure.
These are superconducting magnets, or really, really strong magnets. They've turned these up to 11.
How like on a comparison, like how about compared to MRI? Those are really powerful magnets, we know, right? Like you're not allowed to wear anything metallic when you go into an MRI.
Yeah, you have to, do the check. No rings, no anything.
Right.
These magnets are 10.5 times more powerful than an MRI.
So you can't just throw a strawberry into an MRI and expect it to float. You got to have 10 of them wrapped around that sucker.
All wrapped around each other somehow.
So that's a pretty phenomenal amount of electromagnetic force in order to generate this parlor trick. And it's because of, you were saying earlier that water is a very diamagnetic, am I getting that word right? Diamagnetic material. Yeah. So it is because of the water in the strawberries and the frogs and the crickets and everything that actually causes them, really, it's just the water amount?
Yeah, you think, you've always heard that thing, people are, 1/3 water or, whatever percentage they are. And it's the water in these that sort of, you're putting the lifting weight on the water. Or the water in those objects is sort of pushing.
Doesn't this also mean that those scenes in X-Men where Magneto needs to use the iron in people's blood to lift them, doesn't it mean that theoretically he could have just used the water?
Would have been a lot easier.
Yeah, seriously.
Because there's a lot more water in people than iron.
Now, pay attention, comic book writers and everybody else. Your science is wrong. Now, okay, so that's really cool. I'm looking forward to going through the visuals to splice them down in this episode because I haven't seen those yet. Those videos of the floating crickets and frogs and stuff like that. That sounds awesome. Another really awesome thing, though, is our next question here.
Yes.
One of our viewers wrote in and wanted to know why a cloud forms around like supersonic jets when the sonic boom occurs. Now, in order to answer this, I think that we should take it down to a several-step process. First of all, I think it'd be good for our listeners to kind of explain what a sonic boom is and all that kind of stuff. And then we can get into the clouds. So why don't we start with what is a sonic boom?
So to get to a sonic boom, you kind of have to remember sound travels at a specific speed. Remember, maybe from our lightning episode, that light travels one speed, sound travels another.
And that sound is quite a bit slower than light.
Yeah, only 760 miles per hour. So when an object is passing through the air, the pressure waves in front of the object, think of it kind of like a boat through water. There's waves on the water in front of you and behind you. The same thing's happening in air.
And you can also hear this happen. It's called the Doppler effect. Like, well, the very simple thing that most of us have heard is when an ice cream truck is passing by. When it's coming towards you, it's going dee-dee-dee-dee-dee-dee-dee, and then it passes by and it's dee-dee-dee-dee-dee-dee-dee-dee-dee. It's because of the stretching of sound waves. When it's coming towards you, even though it's not at a very high speed,
they're bunched up together.
Yeah, all the sound waves are closer.
So it's increasing the frequency.
Uh-huh.
And when it's passing back, they're kind of stretched out a little bit. And so it's lowering the frequency and bringing the sound down.
Exactly. So when we're talking about supersonic things, or things that can go faster than that 760 mile per hour barrier, you get to the point where so many sound waves build up that they actually become
all crushed together and break away all in one part. So it's like you're hearing, a minute's worth of sound all in a split second.
Oh, so that's why it booms. That's why it's that actual concentration of sound.
It's dragging, and then it releases and poof.
So that means you can't actually hear a supersonic jet coming, right?
That's a good point.
No, but jets are not actually the first man-made thing ever to be able to break the sound barrier, are they?
No, they're not.
What is, as far as we know?
The first human invention that probably broke the sound barrier is a bullwhip.
Really?
Yeah, the end of that, you know how it cracks?
Yeah.
That's like a little baby sonic boom.
Oh. Because a sudden, okay. Yeah, that makes sense,
it's going
actually.
the tip of it's able to go so fast that it actually can break it just a little.
Wow. But it's so small that it's not like the gigantic
it's not
window
like
earth-shattering boom that you get from...
Yeah, a jet's got a lot of air in front of it that it's sort of build up the sound for and breaks away. The tip of the whip is very tiny.
Now, what about the cloud? Let's get into talking about that a little bit, because we know, does this just come from classic condensation, like the kind of thing that builds up in contrails on jets, or is it something more than that?
Well, they don't quite know for sure. Like, while the origins of this cloud are still debated in some parts of the scientific community, right now the best assumption is that it's rapid condensation of water vapor due to the sonic shock, and it's producing a subsonic shock going slower than the speed of sound. So it's creating this weird cone area where the water can actually condense and sort of create a visual effect.
Well, it's cool, however it happens, so we'll keep looking into that. If we get a more solid answer...
It looks really cool one way or the other.
Yeah. Oh, okay, so that's it for this question. Let's move on to the next one.
Yes.
This one, actually, I got to warn you guys up front, this one's going to get pretty mathy.
Yeah.
But I find it fascinating. And it's not that I'm a total math geek. I mean, I kind of am, but I'm not very good at math. Like above algebra, I'm just really lost. But the next question that we got was, why are there 360 degrees in a circle?
This was really fun to research.
This is also history, too.
Yeah, there's a lot of history involved in it.
Well, why don't you go ahead and give us the rundown of where people think that this probably originated?
Sure. Well, there are a few theories about the origin. Precisely where it originated, kind of unknown, because a lot of ancient peoples were kind of stealing ideas from each other. But we can start with the idea that instead of counting to 5 on one hand, you can count to 12.
Using the finger bones in each.
Finger bones.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
So there's 12 bones, 2 hands, 24 hours in a day.
Okay, that makes sense.
This kind of counting to 12 gave us a base 60 math.
Now,
the name of which you will never forget.
I want to try this here. I don't know if I'm going to get this right, but sexagesimal.
Yes.
I'm also typing it right now, just so you guys don't think that I'm just uttering a naughty word. This is a real term.
This is a real term.
Base 60 math, instead of what we use in modern day for most things is base 10, right?
Yeah.
I'm right, which is decimal.
Yeah, decimal base 10. This is base 60. Well, 12 bones, 5 fingers, 12 times 5 is 60.
Now, who are some of the ancients that use this? Is this like the big ones? Was this like Babylonians?
Yeah, this is the Sumerians, the Babylonians. It's still used in some modified form in parts of Asia.
Oh, that's interesting. I didn't know that. But like you said earlier, this is also it shows that there's some basis, some commonality in the origination, because there's 60 minutes in an hour, 60 seconds in a minute, and actually even in degrees of arc.
Yeah.
There's also, we use milli-arc, or minutes of arc, and arc seconds, which are also measured in groups of 60. Mm-hmm. So, and all of that kind of spills over into the 360 concept, right?
Yeah. Another theory on this has to do with ancient astronomy, noticing that the stars, moved around in a circle around the sky. And they said, oh, so it's like 360 days from one location to the other. They had 360 days as a year.
And that probably felt really convenient to them since they were already using a base 60 math. At least
that's probably why they chose
many
360.
Wow. All of it just kind of fits together like that. Like fingers. Now, but it goes beyond that too, because when we're talking about actual math, geometry, it can work out in different ways. Like there's something about the equilateral triangle. Tell us about that.
The triangle that has all equal sides. The angle of the degree in an equilateral triangle is 60 degrees.
Well, jeepers. It all just makes perfect sense then.
Yeah.
Even though we think of 360 as such a weird, uneven number. I mean, why not just use 100? Just divide it by tens. Actually, I've always thought, why don't we keep time in a decimal system, But I guess this kind of explains it. It does make sense on so many different levels. And
I mean, 360 is easy on the math.
Yeah, you can cut it into so many different even chunks.
Yeah.
So many different ways. So that must have been...
divide it up a whole bunch of different ways. It can do all this other stuff. It has to do with base 60 math, but...
But it's just not decimal, and we like tens, apparently. Unless you're using the imperial system of feet and, well, whatever, inches. We should switch. We should really switch to metric. Or just switch back to sexagesimal. It seems to work so well, right? And it's so easy to say.
Everyone have fun saying it.
All right, well, let's move on to the final. No, not the final. We have two more questions.
There's two more questions.
This episode is so packed with science. And actually, let's move on from the math. Let's leave that behind us because this next one is very sciencey. And I'll just dig right into it. We got a question from one of our viewers. Does science know with 100% certainty that black holes exist? Or is it only like we're pretty sure sort of thing? I think in a nutshell, we can answer that all of science is never 100% sure. And there's always a room for something to be proven wrong. But we do have some very specific ways that we can observe the effects of black holes. It's really interesting. If you don't mind me stealing all of the thunder here, because I did a lot of...
Steal some science.
I love black holes. I think these things are fascinating because they break so many rules. Black holes, as most of you are probably aware, are black because even light cannot escape their pull. But light is not the only thing that can't. I mean, practically nothing can escape the pull of a black hole, which is why they are not observable by direct observation, which is actually kind of similar to dark matter that we were talking about several episodes back.
Yeah.
For different reasons. But so the only way that we can actually, that science can try to convincingly prove that black holes exist is by looking at their effects on other things. But there are a number of things that science has done to do exactly that. Now, black holes themselves are a phenomenon that has basically been proposed in math for at about 150, 200 years. But up until this century, it hasn't been really solidified through an extra series of testings and things like that. But we have had some real science on this subject.
Yeah, it started in the 1970s. They were able to look at this, and through redshift and blueshift, which is, talking about the speed of objects moving.
Which is actually similar to the Doppler effect we just talked about. When light is moving, when something emitting light is coming towards you, the wavelengths get pressed and shift towards... Is that blue?
And they're moving...
I forget off the top of my head.
One way is red, one way it gets stretched out.
Yeah.
Yep. Right. It's the same kind of idea.
Yeah.
So they were able to see this huge amounts of mass traveling towards us really fast in one direction and away from us really fast in the other. Except it was really close together. And they're like, there has to be a huge amount of weight in the middle of that to make it that much mass spin that fast.
And that was one of the first observations that might have conclusively proven that there was something that could meet the description of a black hole.
Yeah.
Right? Now, I want to skip ahead a little bit here because I was reading about an observation that was done actually by the Chandra group, the Chandra Observatory, in 2001. That was also some of the best evidence that we've had so far to prove that black holes actually exist.
Yeah, not only black holes, but their event horizon specifically.
Yes, absolutely. Now, what these guys were doing is they took a whole set of binary star systems, but the binary set of those one was a normal star in all of these sets, and the other half of each of those sets was either a neutron star, which is an extremely dense object, but that we can actually physically observe. We know it exists, absolutely, without a doubt. And the other set was like black hole candidates, things that they thought were probably black holes.
Yeah.
And they looked at the observations of each of these and compared the studies, and it showed that because there was binary systems, all of these dense bodies, whether they were the black hole candidates or the neutron stars, were sucking matter away from the other star in their system. But in the neutron star sets, you could actually see the matter, the energy, being ejected from the surface of the neutron stars in
like
the form of radiation.
A rock at water, the water splashes back up. You could see something splashing back out.
But in every single one of the systems that they were looking at that was a black hole candidate, that energy did not exist. There was an extremely minor amount of energy emitted from what ended up being confirmed as the event horizon of the black holes in these other binary systems. And I've got a picture that you guys have got to see. It's really mind-blowing. And this whole concept, this whole form of observation is called X-ray binary observation. And it's basically a way of looking at the X-rays and the radiation emitted by these to see whether or not you're looking at a black hole.
Yeah.
It's pretty awesome. But it's not the only way that we've determined that we can actually observe the effects, the direct effects of a black hole on its surrounding area. There's also something, I don't want to go too deeply into this because I started the research on Hawking radiation.
Yes.
Boy, I got to tell you,
that is a whole black hole of a topic in itself.
Absolutely.
You're going to dive into that and you're never coming back out.
Yes, absolutely. That could be a whole episode. It really could. It's extremely complicated, very mathy.
Oh, yes.
So I should have dug into it because, it would have gotten my geek on. But it's really not something that we have time to explain to you. But what it comes down to is it's a type of radiation emitted by black holes. But it is, correct me if I'm wrong on this, if I'm understanding this correctly, the amount of radiation emitted by a black hole is directly inversely proportionate to the mass of that black hole, which means the more massive a black hole is, the less radiation it puts out. And every black hole candidate that we're able to observe with our current technology is extremely big.
Yes.
Which means that it puts out an exceedingly small amount of Hawking radiation.
Which is too small for us to be able to detect.
Yes. So, unfortunately, that is the case. Even the math tells us that we shouldn't be able to see it right now based on the bodies that we're observing. But that's not the end of Hawking radiation, because there is something that exists called primordial black holes, which are these tiny little black holes. Blows my mind that such a thing could even exist, but they do, apparently, and the math tells us that they do. But these black holes are small enough that eventually they dissipate. They collapse in on themselves and kind of vanish. But when they do so...
in the meantime, in that collapse, they let off a massive burst of this Hawking radiation.
Yeah, the burst is so massive that it's finally enough that we would be able to observe if we knew where to point our instruments, because, it's not happening everywhere at the right time.
We have the instruments pointed looking for them, but we just have to wait for it to happen.
Including the, what was it that launched the Fermi Gamma Ray telescope in 2008. One of their, they've done so much other stuff working out there, but one of the things they're looking for is this Hawking radiation burst from the collapse of a primordial black hole.
Yep.
So I really hope they find it. Because like I said earlier, I find black holes absolutely fascinating just because they boggle my mind. They break so many rules.
Things that break that many rules are pretty cool.
Yeah. Well, let's talk about something else that breaks the rules, because we have one more question to cover tonight. I don't even know where to begin with the question here. Tachyon particles. The actual question that we got was, do tachyon particles travel backwards in time? And I think before we go actually into just explaining whether or not yes or no they don't, what is a tachyon particle?
A tachyon particle is a hypothetical subatomic particle that moves faster than the speed of light.
I thought nothing could move faster than the speed of light.
That's why it's hypothetical. If it actually follows the rules that general relativity says, then it wouldn't be able to interact with anything, like physical.
So, but if it can't interact with anything, then we have no way to prove whether it exists or not, right?
Yeah, it's kind of part of the catch-22 of tachyon particles.
Well, why don't we even... Okay, I blame Star Trek for this one. All right, well, let's get into a little bit of... since they travel faster than the speed of light, correct me if I'm wrong, but that means that they would technically travel back in time, because time, sort of, space-time moves with the speed of light. That's the barrier. I mean, if you...
Sort of. There's this weird part of it where as it passes you, it's traveling faster than the speed of light. So as it passes you...
You wouldn't see it coming, first of all. because
you
wouldn't
see
see
it
the
coming, but as
light
it
until
passes,
after it
you
had
would actually
passed.
sort of see it split into two. One traveling backwards and one traveling forwards.
Okay.
Crazy visual phenomenons for things that don't follow the light rules.
Just more evidence that this thing should not exist.
Oh gosh, they're crazy.
Let's talk theoretical for just a minute, since tachyons are theoretical anyway. If we could, I don't know, attach some sort of information, some bit of information to a tachyon, or figure out a way to read a tachyon, or, I don't know, utilize them for anything, detect them at all, we would theoretically be able to detect the effects of things on that tachyon that hadn't occurred yet. Right?
Yes.
That doesn't seem like something that we need to be doing in science right now.
You could get the lotto numbers before you send them to yourself backwards in time, but then does that change the lotto numbers for tomorrow? And if you get the answer, do you know the question? And does that change the question? Yeah, things get crazy from there.
But suffice it to say, the answer is yes, kind of. They don't actually travel backwards in time, but the fact that they're traveling faster than light means that they outrun causality. Right? That's a pretty accurate way of putting
it. If we get beamed the answer of whether they exist or not, we'll know.
Yeah. So let's go forward in time and attach the answer to a tachyon, and
then send it back, and we'll know. So why have to do the research for this kind of thing when you can just get beamed the answer from the future?
That's the answer right there. We need tachyonic technology. Screw quantum computing. Let's skip straight to tachyonic. All right. Well, that's all of the Q&A that we have to cover with you guys on this week's episode of SciByte. I did tease at the beginning of this episode that you needed to watch the entire episode to learn a very important piece of information. Unfortunately, I don't know that a lot of you watching are going to be very happy with this information. There's no good way to put this, so I'm just going to come out and say it. SciByte's going on an indefinite hiatus.
Yeah.
That's pretty much the gist of it right now. Life has been too busy around here, as you might have noticed by me having to miss the last couple episodes. But Heather's also up to her eyeballs in scientific... What are you doing, proposals or something like that?
Yeah, proposals for work and hoping to get money.
Yeah, well, science needs money to move forward.
Yeah.
Really, you guys should support science with your dollars, if you can find a way to do so. I support that. Because of that, and because honestly the amount of views that we've been getting is anything, we love you guys that have been watching, and we know that you're very vocal fans. The fact that you guys are sending in Q&A, absolutely thumbs up. Unfortunately, we're just not quite meeting enough of you. So what we're going to be doing is retooling the show a little bit, looking at an eventual relaunch of some sort. But it's not going away entirely. In fact, Heather's going to be sticking around here with Jupiter Broadcasting as a correspondent. In fact, I've already talked to you about potentially showing up on Jupiter at night if we have major science stories to cover. And you're a big MMO gamer, so you'll probably show up with me on the morgue, especially...
Still going to be around. The science goes on. So I won't be getting bored of it anytime soon.
So just look for that. Stay tuned and check us out over at Jupiter Colony if you want to see any updates on SciByte in the future, or just keep talking about science. We're not going to shut down the SciByte sub forum. So if you want to talk to other science fans that have been enjoying the show, absolutely. That is your playground. It's going to stay there for you to play in. And if you still want to get in touch with us, as we said, Heather's going to be around. I'm going to be around. So if you wanted to get in touch with us ever, we're going to keep on the SciByte at Jupiter Broadcasting email address. Oh, I stole your thunder on that one.
You stole my thunder.
But we can go ahead and tell them our Twitters. I am at JB Jeremy.
And I am JB_Marsbase.
And that's it for this episode of SciByte. Now, also, as I said, that means that we're not going to be doing a quantum mechanics episode. Thank God. Oh my God, that was ripping my head place open just thinking about all that stuff. But we will be keeping to do science on whenever we can. So stay tuned and keep watching Jupiter Broadcasting to get your geek on in any way that you can. And until the next time we see you, keep your science hats on as well, because science cannot die.
Never. Never. The water vapor in the condense can condense where it's fairly assumed they let off. Science may have lied to you.
Oh, don't lie to me.
Oh no.
Oh no.